So that actually involves some Chapter 8 material, so I need to talk about Chapter 8 a bit. Chapter 8 deals with electrons and atoms. The first part of Chapter 8 talks about light. So let's take a look at light. Light is electromagnetic radiation. And electromagnetic radiation we think of as being oscillating electric and magnetic fields. Electromagnetic radiation. This is equal to light. There are lots of different kinds of light. But what we see is we're going to have an oscillating electric field. Like this. Oscillating just means it fluctuates between positive and negative. So this would be positive, negative, amplitude. Then we'd have like zero amplitude. Amplitude is how high these waves are, or how high these waves get. Usually the higher the amplitude, the greater the energy. The small wave versus the large wave. And so we'll have oscillating electric fields, which is this positive and negative, so it just oscillates between positive and negative. And we'll have oscillating magnetic fields. The magnetic fields we can think of as being perpendicular to this. But we're going to focus on the electric field portion of this. No, not at all. You can record all of them. It's nice to ask, but you don't have to ask. I don't really care. When I was a student at UCLA, I was only able to, I wanted to record the lectures too. That way I wouldn't miss anything. There was only one class that I was allowed to record the lectures for. Every other class, they didn't let me record the lecture. And that was a history of French film. Being able to record it made it so much easier. That way I didn't have to worry about scrambling to take all the notes down so quickly. But I don't care. Oscillating electric and magnetic fields. The magnetic part, we're not going to really focus on so much. The magnetic is just oscillates between North Pole, South Pole, North Pole, South Pole. So if you had a little magnet and you were experiencing an oscillating field, it would flip the magnet back and forth. Because 1 minute the North Pole's on this side, the next minute's on the other side. So if you're a little magnet, you'd be flipping back and forth. These oscillating magnetic fields are important, because it turns out that a lot of atoms, act like little magnets, like hydrogen atoms, the nucleus, the proton. The proton in a hydrogen atom actually has a north pole and a south pole. It's not just a positive charge. You think of a proton, you just think of a ball or a sphere or something that has a positive charge, but there's actually a north pole and a south pole to it. It's kind of weird to think about. That kind of stuff comes from like the particle physics of it. Electrons also act as little magnets too. So electrons and nuclei can interact with these oscillating fields. This is the whole premise behind magnetic resonance imaging. Magnetic resonance imaging is exposing the little magnets in the hydrogen atoms, nuclei, to an external magnetic field and then flipping them.
Does that magnetic resonance also apply to neutrons? Like, that neutron is zero charge, but does it have a north and a south?
The neutron, actually, I don't know. Neutron. I mean, I know nucleus. And then
electrons and protons can go back to north and south.
Yeah.
So it doesn't matter which one's which. Neutrons do not have magnetic field.
Yeah. Electrons' magnetic field is much stronger. They call it magnetic dipole. And so the electron's magnetic dipole has been known for a long time, but the nucleus's magnetic dipole hasn't, because it's so weak, it's hard to observe.
Can you explain resonance a little bit more?
Resonance is, let's say you have a big heavy magnet. If you have a big heavy magnet and there's a weak oscillating field, there's too much inertia. That big magnet doesn't interact with the field at all. It's like the way people understand resonance is like, let's say you're on a cruise ship and there are a whole bunch of little waves here, but you're on this gigantic cruise ship. Is this cruise ship going to oscillate with these little tiny waves? No, it's not going to oscillate. And so, in that sense, there's no resonance there. But let's say you're on a little boat. If you're on a little boat, will this little boat oscillate up and down with the waves? Yes. And so there we have resonance. And so it depends on the on the strength. So here it can, and it's a little bit weird because you think, okay, a little boat can, but even a tiny boat. What about a tiny boat? Well, you think a tiny boat can as well. But it turns out that there are natural, what we call resonant frequencies for things. Have you seen the Tacoma Narrows Bridge? Have you seen that? Well, they just hit the natural resonant frequency. I guess the wind hit it or whatever hit it. And then once it starts oscillating, then it can just continue to oscillate and build up in amplitude. But things will have different resonance frequencies depending on how they can interact. And so one simple analogy, although it's not perfect, is like this. So if you have a big magnet here, it's not going to oscillate. It just has to be the right size magnet, and then it can flip back and forth. And this is like the hydrogen atom in magnetic resonance imaging. The hydrogen atom, you have to put it in the external magnetic field. Otherwise, the Earth's magnetic field is too weak, and so it doesn't really interact with the Earth's magnetic field. So you put it in a giant magnet, and then not only that, you change the magnetic field strength, and then see how much energy it takes to flip these kind of things. I mean, I'm oversimplifying it. But
isn't that why the sky is blue?
The sky is blue because of
Resonance.
The sky. Well, it depends on how you want to think about resonance and what you think about resonance. It's just the way light travels through different media. That things with it. Yeah, but that's more like scattering. Light scatters like. We'll talk about this. Red light scatters more than, and then blue light makes it there, or that kind of stuff. Resonance. We'll talk more specifically about resonance because we need to understand that. But resonance is not scattering of light. Resonance is actual absorption of the light. And so light is actually being absorbed and causing certain things to happen. And this goes for, since we're interested in electric fields you expect to interact with electrons, right? Now it depends, is electron, what's the electron attached to? We have things that are free electrons. If you have a free electron, then a free electron's free to move, right? And so the free electron can resonate with lots of different waves, And actually, I need to talk a little bit more about this because this electromagnetic radiation is oscillating electric and magnetic fields, but it isn't moving. It's traveling, and it's going to have a velocity. In a vacuum, the velocity is 3 or 3.0 or 2.99 or 2.98. What was it? I forgot the numbers. But the velocity is 3.0 times 10 to the 8 meters per second in a vacuum.
Is that called a photon?
We'll talk more about a photon. But the light would be called a photon. We'll have to talk in a vacuum. In other media, travels faster or slower. So this would give, and it depends on what we call the wavelength here. The peak-to-peak distance here is given the symbol lambda. And that's called the wavelength. Actually, I can show it. And so they have a traveling wave here. And you can see it's oscillating up and down, this traveling wave.
How do you write and
Like
is
this.
that like a
That's lambda. It's the peak to peak or the valley to valley distance. Lambda. We have something called the amplitude of the wave, the amplitude. We can either go from the 0 to the top here, or from the valley to the top here. Amplitude. The velocity is given a different symbol. The velocity is given the symbol c, which is the speed of light. Then we have something called frequency. We talked about amplitude. Amplitude is the height of the wave above the center line or the maximum depth below. So the amplitude is just going to be from the center here. So either this peak here or this valley here. Frequency is given the symbol nu, which looks like V. So if this wave is traveling at the speed of light to me, then what I'm going to observe is I'm going to observe an oscillating electric field like this. It's going to be positive, negative, positive, negative, positive, negative. And an oscillating magnetic field, north pole, south pole, north pole, south pole. And so it's oscillating like this. If I'm an electron, then I'm going to see that because I can interact with this. Right? Because an electron is negative. And so if it's positive, it's like this. If it's negative, it's going to throw it down the other way. It's going to repel. And so the electron's like the little boat. And if the boat is oscillating with the wave, then that's what we call resonance there. However, it depends on what this boat is attached to. Let's say the boat is heavily anchored to the nucleus. If the boat is heavily anchored to the nucleus and a small wave comes, do you think that's going to really impact the electron as much? No. So it depends. And so the electron will oscillate, and that's what we're interested in. We're interested in that. Not only will electrons oscillate, but also polar bonds will oscillate too. And so we have electrons that can oscillate. We have polar bonds that can oscillate. Like say, like a really polar bond like this here, or this. We'll just call it this R. R just stands for the rest of the molecule. So I put an alcohol here. And in the alcohol, I have a delta plus and a delta minus here. And so what's going to happen here is this oscillates plus and minus. That's going to interact with this bond and cause it to vibrate. But not any wave will cause that to vibrate. It has to be right on the resonant, what we call the resonant frequency. If it's not on the resonant frequency, it's not going to be able to vibrate. It's got to have a certain amount of energy, just enough energy to cause that vibration. Too little energy doesn't vibrate. Too much energy, it doesn't either. It has to be just the right amount of energy. And that's what we call resonance, because it has to be just the right amount of energy to cause that to vibrate.
Isn't that what vibrates in water?
Yeah, That's what microwaves, but microwaves don't cause it to vibrate. Microwaves cause it to rotate. And so the rotation is also the same thing. There's some inertia involved in rotating a water molecule in liquid water because liquid water, you have the hydrogen bonding interactions and they're really sticky with one another. So you have to have just the right amount of energy to cause it to rotate. And so microwaves are tuned to that, like 5 gigahertz or something. And so it has just enough energy to rotate this molecule. This molecule is also delta minus on this end, delta plus on this end. So it interacts with oscillating electric fields like this.
So it creates heat.
Yeah, the collisions, it creates kinetic energy and it creates heat. You know? These vibrations have to be tuned just right. In water, there's only 3 vibrations.
When you say like just the right amount of energy, are you talking about the electrons or the waves? Or
The waves have to have just the right amount of energy to cause it to happen. If the waves are too weak, nothing happens. If they're too strong, actually nothing happens. It's kind of weird. You'd think if it's too strong, it'd be just like a tidal wave.
Vibration and going in and out.
There are. You would think water molecules can vibrate in any way, but they can't.
What to use Miro? When you draw on a whiteboard, no one sees it. With Miro, you plan together in real.
I will show you how types of vibration most of the water.
So this specific vibration, the scissoring, it takes a specific amount of energy. This kind of vibration requires a certain amount of energy, and
T and
so
minus
we don't have
the
to.
water is a non-linear quantity. So
Then there's one more vibration. Okay, this vibration, this is the 3rd vibration. There are only three ways a water molecule can vibrate. Those are the 3 ways. Each of those ways takes a specific energy to do that. When you're heating water on the flame, so much of that flame energy is wasted. It's wasted because it's not absorbed by water. You know, you're heating it. When you're heating it on a flame, you're blasting it with a whole range of energies. And it only absorbs 3 of those. So where it doesn't absorb, all that energy is wasted. And so this is the benefit of a microwave. A microwave is just trying to hit one of those energies to cause the rotation so that you don't waste a lot of energy. Because if you're blasting with low energy and too high of energy, all that energy is wasted because it's not going to cause anything to happen. And so that's all part of resonance. And so this is the resonance frequencies, and then you can measure it.
What tool do we use to measure the resonance?
You use what we call infrared spectrometer.
Really?
Yeah. And you generate something called an IR spectrum. And so we can look at the IR spectrum of water. The IR spectrum, these are really weird because they're upside down. This is the IR spectrum of water. These valleys are actually peaks. So this is absorbing here. This one, that's causing one of the vibrations. Actually, there's a very cool animation where you can click this, and each of these you click shows which vibration that corresponds to. This is the other one. This is the other one here. So these are the 3 resonant frequencies in the infrared spectrum of water. Everything else is not doing anything. So waves here don't do anything, and waves here don't do anything to water at all. Those would be wasted because they can't cause those. They don't have the right energy to cause those vibrations to occur here. And so infrared, those are what we call bands, infrared bands or peaks. You know, the peaks are actually valleys. This is just historically done this way. And so this is actually nothing here. This hill here, this plateau is actually nothing here as well as the valleys we're looking at. That's different than most spectra. Most spectra, we look at the peaks, not the valleys. Only the infrared spectrum, we look at the valleys, not the peaks. And so it's different. Uh-huh.
What type of vibration is the microwave do? Like the rotation, what is that? Is that one of the three?
That's not, no. Microwaves don't have enough energy to do this. Microwaves are lower in energy. They don't have enough energy to vibrate, but they have enough energy to rotate. It takes a lot less energy to rotate water than to vibrate it. And so what we look at for microwaves is, I don't know if we're going to see good. So when we look at the rotational, these are called transitions because they're causing things to rotate, in which the molecule gains a quantum of rotational energy. Atmospheric water vapor at ambient temperature and pressure gives rise to absorption in the far infrared region, to longer wavelengths towards the microwave region. And so it's pretty much microwaves. It's kind of at the border between microwaves and infrared. We'll talk about types of light. But this is the rotation of water. This is the rotational spectrum. This is oftentimes they call it rotational vibrational, because what you'll see is not only will it rotate, but it'll vibrate as well, depending on what kinds of energy. And then it's going to depend on what we call the moment, how much inertia, how resistant is it, how difficult is it to do this. And so we look at the structure, we talk about symmetry and this kind of stuff. These are the three fundamental vibrations of water. These are the energies associated with that. So these are the resonant frequencies of water here. We have some rotation.
Do we need to know?
No, we don't need to know.
I have a question, Professor.
Yeah.
Would you say that water is easy to resonate, or is it difficult to resonate?
No, if you have the right energies, then it's easy to resonate. Otherwise, we wouldn't be able to heat water up, or do other things with water.
Yeah, the vibration.
Yeah. So this is going into microwave ovens and rotation of water molecules here. The absorption is used in microwave ovens to heat food that contains water molecules. A frequency of 2.45 gigahertz, that's what it was. Wavelength of 122 nanometers is commonly used. Actually, you could rotate water with others, but as far as microwave generators go, 2.45 gigahertz is very common. This is what we call frequency, gigahertz. And so microwaves in this frequency. Etc.
Professor,
Uh-huh.
if water is easy to resonate with, is there something that's difficult to resonate with? Like, is there kind of a graph to
No.
show a difficulty of
Well,
resonance between materials?
Everything's easy to resonate as long as you have the right frequency. I mean, something that can generate the frequency.
So everything has a similar level of resonance. It just requires different levels of energy or wavelengths or.
Once you hit that resonant frequency, then it's easy to resonate. Once you hit it, but hitting that sometimes might be hard. Sometimes you want to prevent that from happening. So what they do now, at the Tacoma Narrows Bridge, What they do now is they try to find the resonant frequency of those. So they might build a model and then hit it and then see where it resonates, because it's easy to resonate once you hit that. With buildings too. With buildings, they want to know the resonant frequency of buildings. So it's easy to hit it. So what they're trying to do is they're trying to avoid hitting it. They're trying to avoid hitting it by making it difficult to hit under natural conditions. You know, they want to make the frequency so far out the window of normal frequencies, you know, like wind or whatever else, that it never gets hit. And so nowadays they try to find the resonant frequencies of things. So if you take you take a hammer and you hit the table, you think, oh, the table's not resonating, right? But if you hit it with a hammer, then it's giving it a pulse of energy, and with that pulse of energy, then you can determine where it would resonate, like the table. And fortunately, the table's not going to resonate and start oscillating like this under normal, conditions, but under certain circumstances, it will do certain things like that, or could. Well, anyway, so we're going to focus on, the magnetic part is interesting too, because electrons are like little magnets also. And so electrons act as little north poles and south poles, and they can flip as well. Nuclei can act as little magnets, not all, like hydrogen can, and a bunch of others. So we can get that. Okay, so we should talk about that. It depends on the energy. And we have to have just the right energy to cause that. There's a certain amount of energy, minimum required to start vibrating this, or minimum amount of energy that's required to start rotating this. And so we're going to be looking at energy. In physics, we think of the energy as being directly proportional to the amplitude here. The higher the amplitude, the more energy there is. And so we just got to increase the amplitude or decrease the amplitude. Now, in physics, it doesn't really matter what the wavelength is. It matters what the amplitude is, right? Because the bigger the amplitude, the more energy it has. And so all I have to do is I just have to start off at low amplitude and then just keep increasing the amplitude. But if I do that, let's say at low amplitude, this doesn't vibrate. And then I just keep increasing the amplitude, and it still doesn't vibrate. And it turns out that the amplitude, yes, is related to energy, but not in that way. Light, there are two things that impact the energy of light. And we're interested in energy because we want to do things with that light. The first thing is amplitude. And so the original physicists were only interested in amplitude, but it turns out it was wrong. It's not just amplitude. This is what we call classical physics. In classical physics, it's only amplitude. But it turns out it's also related to frequency or wavelength. And this is going to be related to quantum. Actually, amplitude and, let's do this, amplitude and frequency. So basically what had to happen was some adjustments had to be made to physics. And this has happened in the 1900s, these adjustments. Physics has been around since Newton in the 1700s, at least Newton's laws of physics have been around for a long time. And then just more recently, they had to be modified because of certain other things happening. Yeah,
Earth, well, classical physics doesn't even have to be Earth-based. Classical physics was enough to get people to the moon and back. And they didn't really need quantum physics to get people to the moon and back. So classical physics, it turns out that this is it. If you take quantum physics and then you just restrict to large bodies, then quantum physics simplifies to classical physics. You can derive all the laws in classical physics from quantum physics. So quantum physics you can use for everything, but things get complicated. So it's probably easier just to use classical physics for larger bodies, because quantum physics simplifies or reduces to simpler laws. With those simpler laws, then you won't have any problem. So the first thing is, how we deal with energy in light.
Oh, so I shouldn't erase that.
Well, one thing is, it's kind of obvious. Frequency, it's because this symbol, frequency, we can calculate. Frequency is just equal to c over lambda, the speed of light over the wavelength here. And so we could have high frequency, and low frequency. And it depends on the lambda. The shorter the lambda, the higher the frequency. The longer the lambda, the lower the frequency, because both of these are traveling at the same speed, c. So there's no difference in how fast they're going. But the wavelength is going to make things oscillate, slower. So if it's low frequency, it's just oscillating like this. But high frequency, the electron would be oscillating very fast. Here. And so we call this high frequency here. And then this would be low frequency here. And so frequency is inversely proportional to lambda. And so here we're going to have short lambda, high frequency. Here we're going to have a long lambda, low frequency, inversely proportional. And so if you have an electron oscillating like this, very fast, then you would expect that to have higher energy, right? Versus an electron oscillating like this, very slow, that would be lower in energy.
Frequency was proportional to lambda inversely, or frequency is inversely proportional to lambda, right?
Right.
Okay.
Or lambda is inversely proportional to frequency. You could rearrange this. The typical equation is given like this. C is equal to mu times lambda, or lambda mu. This is a normal equation. Yeah. I usually write it like this. Mu is C over lambda. Now, let me ask you about energy. Let's say this is low amplitude. So obviously this should have higher energy, right? Higher frequency, it's oscillating faster, higher energy. Lower frequency, oscillating slower. But let's take a small amplitude, high frequency, versus a large amplitude, low frequency. Which one has more energy?
Low frequency.
They're traveling at the same speed.
They're traveling at the same speed. So which one has more energy?
They're the same.
Would you say they're the same? Because, this is high frequency, but low amplitude. This is low frequency, large amplitude, so maybe they just balance out. Maybe they're just the same, right? Would you think so? So eventually what you could do is, we can figure out what the energy of this high frequency is and then just change the amplitude. This is by turning a knob, turn it to 10. And then we get a higher amplitude, low frequency. And you would think it'd be the same. But so on the one hand, this one should have the higher energy because it's higher frequency. On the other hand, this one should have the higher energy because it's greater amplitude, right? And so it turns out that both of these are correct in a way. And that brings us to something called the when we think about energy, light energy or electromagnetic radiation energy, we have to think in two ways. We think in terms of amplitude. Amplitude is going to be the total energy. And we have to think in terms of frequency. Frequency is going to be what we call the photon energy. The photon is like a particle of light, except light is not matter. Light doesn't have rest mass. And so it's not really a particle. Yeah. Well, they call it like a packet of light. It's like a little packet of light. Maybe that would be. But a lot of people just say particle of light or light packet. This is best illustrated with the photoelectric effect. Einstein won the Nobel Prize, but did he win the Nobel Prize for the special relativity or general relativity? Or is E equals mc squared equation?
Those would all be very good things to win that Nobel.
Yeah, those would all be good things to win the Nobel Prize for. Well, here are the fields. They're showing the magnetic field perpendicular to the electric field. Right. And so I tried to draw perpendicular. Frequency, these are the units for frequency. I didn't talk about that. The units for frequency are seconds to the -1, which is called a hertz. So 1 hertz is what we call 1 over a second. It's 1 cycle. We call it 1 cycle per second. That would be a hertz. Here's the speed of light to many sig figs. 2.9979245 times 10 to the 8 meters per second. Here's the equation that relates frequency, wavelength, and the speed of light. C equals nu times lambda. The speed of light is commonly rounded off to 3.00 times 10 to the 8 meters per second. 3.00 gives you 3 sig figs. Here are some common wavelengths. Centimeters. Microwaves have wavelengths on the order of centimeters. Microwaves don't have, microwaves are kind of interesting. Microwaves have what's called a standing wave. So this is a standing wave in a microwave oven. And if we have 0 amplitude, there's no energy there. We have to have some amplitude there. And as I recall, what is the wavelength of a microwave? So if a microwave operates at 2.45 gigahertz, what is lambda equal to? Can somebody calculate that for me? So a microwave oven is operating at a frequency of 2.45 gigahertz. Then the lambda is, you could use 3.00 times 10 to the 8 meters per second for the speed of light. And then giga is how many hertz? Is it 10 to the 6 is mega. And so what comes after mega? Giga, so it must be 10 to the 9th. And so I would do 2.45 times 10 to the 9th seconds to the minus 1. The unit should work out. 3.00 times 10 to the 8 meters per second, and we're going to get the lambda in meters. And so this is going to be 2.45 times 10 to the 9th seconds to the minus 1. That means cycles per second. One down, up cycle in a second. Divided by, C divided by this. 3.00 times 10 to the 8 meters per second. The seconds cancel out, and that leaves us with meters. And so how many meters is that?
Why don't I put it into my calculator? 1.2244 times 10 to the 17th.
There's a calculation error.
Yeah. Let's try this.
Try to get.
0.1224.
Yes, it's much better. 0.12
1, 2,
2
up to
2
4.
4. Okay, that's enough.
Oh, okay.
Meters, which is 12.2 centimeters. And so in a microwave oven, the wavelength, it's a standing wave. It's not traveling. It's a standing wave inside the box. The standing wave just means it's stationary there. And you have a wavelength of 12.2 centimeters. That means in the microwave oven, you're going to have some cold spots. Do you know you're going to have some cold spots? You're going to have cold spots where you have zero amplitude. Here's going to be a cold spot, and here's going to be a cold spot, and here's going to be a cold spot, and here. So with the microwave oven, it's best to rotate your food, when you're cooking it, or rotate it, periodically as it's cooking. Otherwise, parts of your food are going to be in a zero amplitude, where there's no. Does that make sense?
Yeah.
And so it's because it's 12.2 centimeters, so you move it around a little bit, so you're not in a cold spot. Yeah, so you might have a frozen spot and a hot spot if you're cooking frozen. If you're reheating, it's maybe not as noticeable. So I'm going not in quite the order. No, we're going to come back to Planck's constant. We want to talk about this. When we're talking about energy of light, we think in terms of amplitude. Well, amplitude makes sense. Big wave, small wave, that makes sense. But in classical physics, that's all they thought. The energy of wave is just only proportional to its amplitude. In quantum physics, it became a little different here. And this came about due to the photoelectric effect. So the photoelectric effect tells us the other way we should think about light, and that is the photon. And so it says here Heinrich Hertz. Hertz is frequency units named after Heinrich Hertz here. But we need to know about the photoelectric effect. Discover that when light strikes surface of certain metals, electrons are ejected. Okay. The number of electrons emitted depends on the intensity of the incident light. Well, intensity is amplitude. So when we think about amplitude, that's the same thing as intensity. But the kinetic energies of emitted electrons depend on the frequency of the light. And so it's amplitude and frequency. So how should we understand amplitude and frequency in terms of light? These observations, especially the dependency on frequency, could not be explained by classical wave theory. In other words, these could not be explained by classical physics, because in classical physics, you only care about the amplitude, not the frequency. However, Albert Einstein showed that they are exactly what would be expected with a particle interpretation of radiation. Particle interpretation, this is what I call the packet of light or the photon of light. So if we think of light as coming in little packets, these packets are like particles of light, then it makes sense. In 1905, Einstein proposed electromagnetic radiation has particle light qualities, and that particles of light subsequently called photons by G.N. Lewis. Actually, G.N. Lewis, that's interesting. G.N. Lewis was a professor at Berkeley, and very famous professor. Have a characteristic energy given by E, the photon, is equal to h nu. So in other words, this is the way we got to think about light. So when we think about light like this, there are two ways of thinking about this. Here, what would you rather be hit with? A tidal wave of ping pong balls or a tidal wave of bowling balls? Yeah, you'd rather be hit with a tidal wave of ping pong balls. Well, let's say they both have the same amplitude. They both have the same amplitude, so what would that result in? Well, it would look something like this. Actually, they both have the same amplitude, and for sure, a tidal wave of ping pong balls would be much better. And so what you would think is the ping pong balls consist of a lot of little tiny ping pong balls, and none of the ping pong balls weigh very much. So you have a bunch of little ping pong balls here. Like this. But how would we represent the bowling balls? Well, the tidal wave of bowling balls, we would have the same number of bowling balls as ping pong balls to have the same? No, you'd probably have fewer. And so the way we would represent the tidal wave of bowling balls is there'd be a lot fewer of them, but each one of them would pack significantly more punch. And so what we need to do is we need to reshift our thinking. And so we need to not interpret it like this. We need to change or shift our picture in this way. The photon energy is going to be given by this equation here. E of the photon is equal to h nu. H is a constant. This is Planck's constant. Planck's constant is this comes out of the physics of this, but it's a number that some people memorize.
What is the number for this constant?
6.626 times 10 to the minus 34. I had it memorized for many, many years. It's because you just use it a lot. You don't really have to have it memorized.
Is that joules per second?
No. It's joules times second. It's a,
joules times second.
yeah, it's a very weird unit. This is Planck's constant here. 6.62607 times 10 to the minus 34 joules times seconds. A joule times a second is the unit of what we call action. It's an action unit. And so it's a weird unit. Joule per second is called a watt. Joules times seconds is the unit of action. Joules per second is a power unit. And so it's a weird unit. And so that gives us E of the photon. This is the photon energy here is equal to h nu. Since we know that nu is related to lambda, this is also equal to hc over lambda. So these are the equations. So it tells us that energy is directly proportional to frequency. The higher the frequency, the higher the energy of light. And it's also inversely proportional to lambda. The longer the lambda, the lower the energy of light. And so let's take a look at the photoelectric effect. Metals have loosely held electrons. And so if I look at something like potassium metal is a great reducing agent. It's a great reducing agent because electrons are pretty loosely held. The electrons can easily be taken by oxidizers, but they can also be easily knocked off by light. And so let's shine some light on here. Actually, visible light is enough to do this. This is a photoelectric effect because we can take visible light and knock electrons off. For example, aluminum has much more tightly held electron, so visible light will not knock electrons off aluminum and oxidize it. But potassium, yes. So potassium metal, we need to protect from visible light. Is if you shine visible light on potassium, it becomes oxidized and starts to corrode away. And so normally we store potassium in a dark container, like an amber container. But anyway, we can let's shine green light on this. And green light's enough to oxidize it. In fact, we can figure out what light is. So we'll shine green light on this, and what happens is when the green light strikes the surface, an electron gets ejected. That is, we ionize potassium. Great potassium ion. Okay, so electron gets ejected there. if we shine, let's say we shine 10 watts of green light with a 10-watt light bulb. Okay. We'll eject an electron. What if we shine 100 watts of green light? If we shine 100 watts of green light, what do you think is going to happen?
We will have 10 electrons get knocked off.
Yeah, we'll have a lot more electrons get knocked off. The number, I'm just using one electron just as representative. You'd have a lot more electrons get knocked off than one. But in this case, we're going to have a lot more electrons, right? Get knocked off. And so the difference between 10 watts and 100 watts is the amplitude of that. So we see here that 10 watts of green light was enough. But what if we try to shine 10 watts of red light? So if I try to shine 10 watts of red light, is that enough? Well, what's the difference between green light and red light? Red light has a longer wavelength and a lower frequency. So 10 watts was enough. 10 joules per second, this would be joules per second, was enough. And so I would expect 10 watts of red light, 10 joules per second to do the same thing. What happens is nothing was ejected. No electrons were ejected. Well, this is strange because it's the same power. So we'll bump it up to 100 watts. With 100 watts of red light, what do you think happened?
Well, we can assume that with the lower frequency from red light and the 100-watt increase for a 10 increase, we may reach the minimum threshold for green light.
Yeah, right. You figure if we go to 100 watts, then maybe that will make it happen. 100 watts, do we see the photoelectric? No. Nothing happened here. Let's go to 1,000 watts. What do you think happened with 1,000 watts? Nothing. Nothing happened. With 1,000, although it get very hot. You know, if you have 1,000 watts, it's going to get very hot, and then maybe, you know, but it wasn't enough to eject electrons. It just got very hot.
If it reaches a million, then it will most likely melt.
It'll most likely melt, but it doesn't eject. That's a problem. We're looking at ejecting electrons. And so the way that people visualize this is like a red photon is like a ping pong ball. So 10 watts is not that many ping pong balls. So we're shooting a lot of ping pong balls at the surface. Okay, so we go to 100 watts. We shoot a lot more ping pong balls at the surface. But are the ping pong balls going to do anything? That's not enough. Then we go to 1,000 watts, which is like a huge number of ping pong balls, but is that huge number of ping pong balls going to knock any electrons off? No, so we could even go to 1,000,000 watts, which is totally melt it, but are we going to see? No, because it's just like being hit by tidal wave ping pong balls. I don't think you have to worry too much about getting hurt.
You had said earlier that aluminum is not as easily, does not have electrons that can be as easily knocked off as potassium solid.
Yeah.
If we can't use visible light to strip the electrons off, is there something more powerful than visible light?
Yes, there is. Do you know what's more powerful than visible light? No. Do you know the electromagnetic spectrum? We're going to talk about this in just a minute, but the electromagnetic spectrum, at the end of visible light is the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Violet is the highest energy visible light. Violet has the shortest wavelength, highest frequency. So what's on the other side of violet?
Red.
Not red. Red's on the other end. Red's the low energy end.
Oh, yeah, you don't just go from violet to magenta, right? Go right.
No,
back
no,
to the
we're already past that. We're already past that because we go through all the colors. Is there anything on the opposite side of violet? Ultraviolet. Ultraviolet light will knock electrons off aluminum, probably. Or if not ultraviolet, then
ultraviolet.
yeah, but ultraviolet doesn't go by ultraviolet. Do you know the name for ultraviolet light? It's X-rays. X-rays. Yeah, and then gamma rays would be ultraviolet. And so it doesn't matter what the amplitude is. In physics, we can just match the amplitude and it should have the same energy. That's classical physics. But we have to, when we think about light, we have to think about these two things. We have to think about the photon energy and the amplitude. And so there are going to be two energies that you deal with always when you deal with light. The photon energy is the energy of the individual particle or packet of light. I'm just representing these as dots. And the photon is going to have the energy of the photon equal to h nu, which is equal to hc over lambda. Then we have the total energy. The total energy is equal to the sum of all the photon energies. And so it depends on how many photons you have. You just sum them up and then you're going to get the photon. The total energy. The total energy is usually given in per mole. It's usually, it can be either intensive per mole or extensive. Joules, how many joules do you have, or kilojoules. And typically, when we do the total energy, we'll do kilojoules per mole of photons. And so it's total, it can be intensive. That would be kilojoules per mole of photons. Or it can be extensive. Extensive would just be joules or kilojoules. Normally it's in joules when we talk about that. And so the difference here is this. The photons of red light are just not strong enough. Whereas the photons of green light pack a bigger punch. So if we have the same amplitude, we're going to have a lot fewer photons here. Each photon is going to be a lot bigger in terms of energy. If we have the same amplitude here, again, we got to compensate by having a lot of photons here. And so here, when the green light strikes, it's going to strike with the same energy as the red light, 10 watts, 10 joules per second, 10 watts, 10 joules per second. But in the case for green light, we're going to have fewer photons, and each of those photons is going to pack way more punch. In the case of red light, we're going to be hit with lots of little photons, and these little photons don't have enough energy to do anything. Because what we got to do is we got to oscillate. That is, the other way of thinking about this is we got to oscillate the electron enough that it breaks free. These can oscillate the electron, but not enough. This is why it gets hot, but it doesn't ionize. We need a certain amount of energy to ionize it. And so that's the photoelectric effect. This is Planck's equation. This is one of the big equations of quantum mechanics here. E equals h nu. E the photon is h nu. So let's take a look at the electromagnetic spectrum. So I jumped ahead here. And jump back. This is the electromagnetic spectrum, and you should know this. There's a huge range of frequencies. You can see here. The electromagnetic spectrum consists not just of visible light. The visible light is the light we can see, but there's also invisible light that we can't see. These would be radio waves. Radio waves are electromagnetic radiation. They travel at the speed of light. The difference between radio waves and visible light is the wavelength. The wavelength is much, much longer. If we look at the wavelength is, let's say, 10 to the 4th meters. You know, it would be like 10,000 meters, 100 meters, 10 meters. So we're looking at 10,000 to 10, or about a meter in length. If we have a wavelength of 10,000 meters, its frequency is about 10,000 hertz. There's 10,000 of those come by you every second. When we go to about 1 meter of wavelength, we're looking at like 10 to the 9th hertz. 10 to the 9th hertz is gigahertz, so it's getting into microwaves here. But here we have 10 squared, 100 meters, we got, that's megahertz. So when we look at AM radio is in the megahertz range. Megahertz is around 100 meters wavelength. And so that's 1,000,000 hertz. So you have a wavelength that's 100 meters, and then you're going to have 1,000,000 of those pass by you in 1 second. It's just hard to comprehend. But that's because light's moving so fast. Okay, so we go there, and then we have radio waves, and then microwaves. Microwaves have a little higher frequency, a little shorter wavelength. Wavelengths on the order of centimeters here for microwave. Then we go to infrared. Infrared has wavelengths on the order of micrometers. Then we have visible, and visible has wavelengths on the order of hundreds of nanometers. And then ultraviolet, X-rays, gamma rays. So this is the electromagnetic spectrum here. And gamma rays have extremely short wavelengths. You know, how big is an atom? You know how big an atom is? 1 to 6 angstroms. Angstrom is 10 to the minus 10 meters. So an atom is about here. So X-rays have wavelengths on the order of an atom, but when we get to gamma rays have wavelengths shorter or smaller than atoms. Interesting. But anyway, let's take a look at these energies here. In more detail. We're going to start off with the lowest energy light. The lowest energy light are going to be the radio wave. I'll just write it at the bottom and then we'll go up in energy. If we go up in energy, we're going up in frequency, but we're going down in wavelength. And so the energy and the frequency increase as we go up, but the wavelength goes down as we go up. So you should know we have radio and then what? Microwave. And then what? Infrared. Remember, one way to remember that microwaves are weaker is it takes less energy to rotate a water molecule than to vibrate it. And so microwaves don't have enough energy to vibrate, but they have enough energy to rotate, whereas infrared has enough energy to vibrate. And so infrared or heat lamps can vibrate a matter. And then when we go from infrared, then we're going to hit visible light. Visible light is going to consist of red, and so infrared goes to red, and then orange, and then yellow, green, blue, indigo, and violet. The visible spectrum is actually quite small. If you look at it, the energy range and the wavelength range is very narrow here. The frequency range is very narrow. But I just spread it out and then we can have all the colors here. This is the part that we can see. And so what you should know is this. You should know the range. Red has a wavelength of 760 nanometers at the border. So right at the border between red and infrared is 760. So if we go to a little longer frequency, infrared's in the thousands of nanometers usually. So if we're at 800 nanometers, we're in infrared and we can't see it. And so when we get to about 760, then we can see it. Some people can see it to this. Some people aren't going to be able to see it until maybe orange or something. You know, and then we can see it all the way to the edge of violet. Where's the edge of violet at? The edge of violet's at 390 nanometers. So essentially it ranges from 400 to 800 nanometers. So this is about 400 to 800 nanometers.
Is that the wavelength?
This is the wavelength, yeah. Visible light we usually characterize by lambda, the wavelength. Radio waves we usually characterize by the frequency, 90 megahertz on the frequency dial. That's because this is a matter of convenience, rather than saying 1,000 meters on the wavelength or something like that. You could say that. And so where's green approximately? Well, no, I mean, well, using this, you'd say maybe green is halfway between, which is, well, indigo and violet are kind of together. And so we'll look at that more. Maybe 600 is a guess, something like that, but it's off. It's off because indigo and violet are kind of compressed. Okay, after violet comes what? Ultraviolet. Ultraviolet is usually abbreviated UV. Infrared is usually abbreviated IR. Microwave, they don't have a nice abbreviation for that. And then after ultraviolet is X-rays. And then gamma rays. Gamma rays would be the highest energy. So X-rays and gamma rays we call ionizing radiation, and ultraviolet to some extent we call ionizing radiation. And so let's take a look at radiation and matter briefly here. Radiation and matter. What radio waves do is they excite electrons in metals. Metals have easily excitable electrons, so it doesn't take much frequency to excite those. And so if you have a radio, the old radio antennas, nowadays are different, but the old radio antennas, if you look at an old car, it has a little metal pole. The metal pole acts as the antenna.
On that chart, it looks like gamma rays and X-rays have a significant overlap. Is it possible for something to be both?
Yeah, they do look like they have significant overlap, don't they? Yeah. I guess it's that's a good question. That it's a little that goes to where people say the border is. For example, the border here between violet and ultraviolet is pretty well defined, and people agree on this. Although, it depends. Some people say, no, you can't see all the way to 390. Therefore, you should make the border maybe 400 or something like this. And the same thing with red and infrared. And there's when you see this kind of overlap, it's typically a result of people not agreeing what the border is. You know, and some people say, "Well, really, should you call that a gamma ray or should you call it an X-ray?" Because there's a distinction there, but it's more of a gray area that, you know, what's the difference? And then some people say this, what's the difference? You know, I was just watching a talk on statistics, and they're saying, okay, if you have a 0.05, you know, which is like 95%, you know, as being the border between being statistically significant and statistically insignificant. And then they're saying, well, what if you have a 0.055? Is that all of a sudden statistically insignificant, whereas this is statistically significant? You know, it's ridiculous, they were saying. And since it's ridiculous in that sense, well, it does make sense because this is published, this is not published. And so, you know, all of a sudden this is thrown into the garbage kind of thing. And so people were complaining about that. And this was the same, and historically, somebody might, you know, and historically, there's also origins. You know, certain like nuclear processes give way to gamma radiation, and historically it's been, and so it's associated with that process. And so you don't want to say, okay, this process gives way to both, you know, X-rays and gamma rays. I guess you could say that, but you know, there are other implications to that. And so there's things where you see that, you know, it's not like a solid, clear-cut boundary.
Okay, thank you.
And the same thing with this. You know, it excites electrons more so in certain metals than other metals, you know, depending on how tightly or how loosely those are held. But all metals have pretty loosely held electrons. So if you shine electromagnetic radiation, you're going to get oscillating electric field, plus, minus. And you have electrons in the antenna, they're going to start oscillating with the field. That's resonance here. And the electrons in metals are so loosely held, they can oscillate with lots of different radio frequencies. But you start shining microwaves on a metal, what do you think happens? Have you ever put metal into a microwave? Sparks. Yeah, don't do that because microwaves excite the electrons a bit too much. And so microwaves can ionize electrons in metals. Or if you put a ceramic, let's say your ceramic contains lead. If you put lead ceramic, it's going to get super hot because lead has lots of electrons which can oscillate with the microwaves, and it's just going to get hot because you're not going to ionize them, but they're going to get very excited. And so you could burn your hand by grabbing something with, or cobalt or any of the other metals that have a lot of electrons in there. So you put a cobalt glazed ceramic in there, it's going to get very hot as well. And so this ionizes electrons in metals or rotates small molecules. Microwaves are well known to rotate, and so a lot of, you know, astrophysicists, astrochemists look at the microwave spectrum, you know, and they're looking for small molecules out in space and this kind of stuff. So rotate small molecules. And there are people who just focus on microwave spectroscopy. You know, they're very interested in these rotations. Infrared. This causes vibrations. Polar bonds vibrate. So, you know, we're thinking about global warming, that kind of stuff. You know, greenhouse gases. Like water would be a greenhouse gas. Water can absorb infrared, right? Water absorbs infrared, causes vibrations. It's a greenhouse gas. Methane's a greenhouse gas. Methane has more vibrational modes, you know? And so methane is an excellent greenhouse gas. CO2 is a greenhouse gas, not as good as methane. Probably not as good as water. But what about nitrogen and oxygen? Are nitrogen and oxygen greenhouse gases? No, nitrogen and oxygen are not greenhouse gases. Why? Why don't they absorb infrared? Can you think of a reason why? Yeah, they don't resonate with it, and there's a reason they don't resonate with it. One big reason they don't resonate with infrared radiation is not their size. They're not polar. Nitrogen and oxygen are not greenhouse gases, fortunately. Otherwise, they'd keep in heat. And so they don't have a greenhouse effect. And so this causes polar bonds to vibrate. Red, orange, yellow, green, blue, this excites electrons in colored matter. Excites electrons in matter. Not all matter, you know, there's certain matter that's colorless. And so, like something that's totally clear, colorless, like the plastic here. This plastic isn't interacting with any red, orange, yellow, green, blue, indigo, violet photons, you know, because it's colorless. And so it doesn't resonate at all. But lots of other colored matter will resonate. Like this black. Black, you know where black comes from? Black comes from absorbing all the colors, rainbow. And then white or colorless objects, they don't absorb any colors of the rainbow. Purple. UV breaks bonds, covalent bonds. Some of these will break bonds, like really weak bonds, like iodine, hydrogen peroxide. Hydrogen peroxide, that bond's so easy to break. Hydrogen peroxide, you only need like yellow or green to break that bond. You know, so if you have hydrogen peroxide, you have to protect it from light. Otherwise, light will decompose it. But most matter requires more energy. And then X-rays and gamma rays, this knocks electrons. This ionizes electrons off matter. From matter. Ultraviolet can also ionize. You know, some of the easier stuff to ionize can be ionized with ultraviolet. And so there's overlap here as well, but not really going to worry about it. So today, what we're looking at is this.
Can I get a picture?
Yeah. What does sunlight consist of?
Sunlight can consist of IR, visible light, and UV.
Yeah. When we look at sunlight, sunlight's mostly like infrared. Infrared, you can't see it, but you can feel it. Everybody has an infrared detector. So if you're standing in the shade and let's say there's sun over there, you stick your arm out, you can feel it, right? It's heat. But it's heat in a different way. It's not hot air that you're feeling, right? It's infrared radiation you're feeling. Versus hot air, even if you're standing in the shade, it'd be hot in the shade, you know? But on a cool winter day, it's cool in the shade. But, you can feel that. So everybody has an infrared detector. You can just feel the heat, right? And then we can see the light here. And then there's ultraviolet light. Ultraviolet light is, we don't want too much ultraviolet because ultraviolet breaks bonds. It causes damage.
Sunburn.
Yeah, sunburn. Yeah, you get terrible sunburn. Actually, and it's changed quite a lot. You know, back in it's the ozone. The ozone layer helps protect us from the ultraviolet, and the ozone layer has been significantly depleted. So nowadays, you have to wear a lot more sunscreen. You know, many decades ago, you didn't need to wear so much sunscreen to go out. You wouldn't get burnt so badly. But nowadays, it's important. Yeah, sunburn. So that causes a lot of damage. It breaks bonds. Where does that light come from? It comes from the sun, but how does the sun produce that light?
Fusion.
Yeah, nuclear fusion, fusion energy. And so let's look at producing, that's called emission of light. And let's look at lamps and the emission of light. Versus absorption of light. You know, certain things absorb light, like, you know, this black cap on the pen, that's not emitting any light. You know, if I turn off the lights, I can't see it. But this is absorbing light. In fact, this is absorbing all the colors of the rainbow. That's why it looks black. And this white object here is not absorbing any of the colors of the rainbow, so it looks white. But this blue here, this is absorbing some of the colors of the rainbow. So if I have blue, if something looks blue, there are different ways that color. Indigo violet we put together. And so this is the color wheel here. And so one way to make blue is to absorb all the colors of the rainbow except for blue. If we absorb all the colors of the rainbow, then all we're left with is blue, and that's what we see. The other way of making blue is to absorb orange. If we absorb orange, then all the other colors kind of average out to blue.
Complementary colors.
Complementary colors, exactly. But it doesn't have to be orange. We could, for example, we could absorb red, yellow. If we absorb red, yellow, it'd still look blue. And so that would be absorption. But we're going to look at lamps and light emission. So what does the sun consist mostly of? Gas. Gaseous hydrogen molecules or hydrogen atoms? It's a fuel for the sun. The situation in the sun is it's so hot, there's so much energy that if there were molecules of hydrogen, there are collisions and the hydrogen atoms break apart. When the hydrogen atoms break apart, we make atomic hydrogen. Hydrogen prefers to form molecules, but there's just too much energy, and the molecules are not stable. What does a hydrogen atom consist of?
One proton.
It consists of one proton and, well, most don't have neutrons. One electron, one proton, and one electron. When we think about the energy of a hydrogen atom, what comes to mind? Well, there's a nucleus there. The nucleus is kind of massive. It has a lot of inertia. So the nucleus doesn't really interact much. You know, if we're thinking about the ocean waves, you know, the nucleus is kind of massive. It's like the big ship, and the big ship isn't going to notice it. But the electrons are really light, and so those are going to be influenced by the waves much more. But when we think about the energy of a hydrogen atom, then we want the internal energy of the hydrogen atom. The internal energy is going to consist of potential energy. Potential energy is the potential energy holding the electron to the nucleus. That is the negative and positive Coulombic attraction there. That's potential energy. If I rip this off, then that's going to cost me energy. If I bring it back down, then that's going to release energy. It's potential energy. So there's potential energy holding the electron to the nucleus. And then we have what? The total energy is equal to the potential energy plus the kinetic energy. And so what that means is the electron's moving. It's going to be moving with some kind of kinetic energy. And it's being held to the nucleus by potential energy. So most people visualize the electron as orbiting around the nucleus, like planets kind of orbit around the sun. And so we have that. Now, if I increase the energy of the atom, or in this case of the electron, because that's where the energy is going to go to. If I increase the energy of the electron, then what can I do? Well, I can make the electron move a little faster. If it moves a little faster, then it'll orbit a little bit farther out, or a little bit higher in energy. And so I'll just increase the speed. You know, the faster the electron's moving, the further out it's going to orbit. And the slower the electron is moving, the closer in it's going to be. Now, are there any speed limits for the electron?
Yes.
What's the speed limit?
That's the speed of light, right?
Well, yeah. Ultimately, that's the speed limit. Eventually, you get the electron moving so fast that it
breaks and it
yeah,
separates.
right. It separates. We ionize it. So that's going to be the maximum speed. That energy is well known. That's called the ionization energy. But below the ionization energy, can the electron move at any speed and orbit any orbit it wants? Well, yeah, you already know the answer, but in classical physics predicts this. Any speed up to that limit of ionization, any speed, any orbit is possible. And so what happens is it doesn't stay there forever. And so what happens is this. Let's say the electron's normally happiest here. We call that the ground state. And so the electron's happiest here, that's the ground state. And we write this in terms of an energy level diagram. This is the energy here. And so the electron's happiest at the ground state. If we excite it a little bit, it gets excited, moves faster. But it's not going to stay there forever. And so it gets excited, eventually it drops down. Now, first law of thermodynamics says that energy is conserved. So this could absorb kinetic energy, and when it drops down, it could release electromagnetic radiation, that is light energy. And so this could be infrared here. And we could get all different wavelengths of infrared. You know, there's not just one wavelength or one energy, there's a range or a band that we call infrared. If we excite the electron a little bit higher, then we can start emitting red light when it drops back down. It doesn't stay there forever. It's going to drop back down to what we call the ground state, and then this is what we have emission. And so the electron absorbs energy, and it doesn't have to be light. It could be light, but when it drops down, it emits energy, and this would be red. And then it could absorb even more energy. If it absorbs even more energy, then it could emit red, yellow, orange, green. And so it can emit green, to be a little higher in energy. Blue. You know, in other words, we can just continue exciting the electron to higher and higher energy. And what we should get is something called a continuous spectrum of light. That's what the sun gives us. The sun gives us a continuous spectrum. In other words, all the colors of the rainbow. So we should be able to do the same thing here on Earth. All right, this tube here is filled with hydrogen gas. And then we're going to excite the electrons with a little electric current. It's like when you see a lightning bolt, you know, this is electric current there, high voltage. And so what we're going to do is we're going to make a little lightning bolt here. When you see a lightning bolt out in the sky, what color is a lightning bolt? It's white. And that's white. It's not this kind of white, the box. That's light emission. It's emitting white light, which means it's emitting what colors? All the colors of the rainbow. And that's what we call a continuous spectrum. It's white light. So what I'm going to do is I'm going to make a little lightning bolt in here. And then we should get white light. You know? Let's see. Does that look like white light? No. It looks like purple light. So I'll crank up the voltage. Crank it up even higher. Do I get white light? No. Purple. It's going to be brighter. And then I crank up the voltage more. Do I get white light? No. They couldn't get white light. You can't get white light from this. Can't get white light from that means there's something wrong with classical physics. Because classical physics says that the electron can get any energy it wants. And so classical physics predicts a continuous spectrum. A continuous spectrum would be white light, all the colors added up. But we don't see white light. And so there's something wrong with classical physics, because no matter what they did, they couldn't get the predictions to match the observation. And so we didn't see a lightning bolt there. But why do we see white light from the sun, which is hydrogen atoms? And why do we see white light from a lightning bolt?
Because the energy is so high.
Well, okay, let me answer that question. Why we see is because the energy is so high. The energy is so high that not only do the molecules break apart, but you know what else happens? The electrons. In the sun, the energies are so high, all the electrons get knocked off. And they're no longer attached to hydrogen atoms. In other words, they're what we call free electrons. If you're a free electron, can you go any speed you want? Yeah, you can go any speed you want. Therefore, you can have any kinetic energy you want. Therefore, you're going to emit this whole spectrum. And the same thing in the lightning bolt. In the lightning bolt, that's so hot that we have free electrons. And so the problem here is this. This is the problem. Why is it that when the electrons are stuck on the atom, they can't have any energy, but when the electrons are free, they can have any energy? So free electrons can have any energy, but these electrons that are stuck on the atom should be able to have any energy. That is, they should be able to orbit any orbit they want. But what's observed is this. What's observed is they can't orbit. There are a whole bunch of dead zones here where they cannot orbit. And so they can orbit here, but they can't orbit anywhere between here and here because this is the next allowed orbit. And this whole area is forbidden for the electron to be in. Why is this forbidden? What's causing the electron to be forbidden from this region? And then the next allowed region is way out here. And so this entire area here is forbidden. So if the electron were to go from here to here, it has to jump over this forbidden region in terms of energy. And then the same thing here, from here to here, it has to jump over the forbidden region. So what is causing these forbidden regions?
The other electrons?
Well, there's only one electron here in the hydrogen atom. So I'm writing two, but there's only one electron in hydrogen. So if the electron leaves here, it goes here. Well, what's causing it wasn't, have you ever heard of the postulates of quantum mechanics? We're getting away from classical physics. Classical physics can't explain this. And therefore, classical physics had to be modified. So classical physics was modified, and the first modification was by Bohr. I'm going to stop here. The first modification was by Bohr. And Bohr just said, why? The answer is it can't, because it's not observed. You know, and science is about observations, and that's what's observed. So what we're going to see is this. We're going to take our spectrometer, and you could do this. You can go outside and look at the full rainbow of colors. Don't look directly at the sun, but look through here, and then you can point it at the sun. The light is going to come through this square hole here. And so go outside and take a look at the continuous spectrum of colors from the rainbow. Then we're going to look at different light sources. We'll look at the fluorescent lamp, and then we're going to look at the individual lamps we have set up here. And then what you're going to do is you're just going to kind of sketch them and see what colors are allowed and what colors are forbidden. That's it. And then maybe you can measure the wavelength. On the bottom here is the wavelength in hundreds of nanometers. So we're going to measure the wavelength. Light varies, visible light varies from 400 to 800 nanometers. And so go outside, take a look at the sun's solar spectrum, and then take a look at some of the light sources we have here. The sun, all the colors are allowed. For these lamps, not all the colors are allowed. And we got to figure out why. Okay. This is experiment 3, yeah, I think. So all you're going to do is you're going to take a look at the lamps and do that, but we're also going to weigh our samples. What do you want to do? Do you want to do the light first and then weigh the samples? Or weigh the samples first? All right, we'll weigh the samples first and then we'll look at the lights.